Hello community, we have a new development. When we have our pre-trained LLM, we used to do a supervised fine-tuning in a DPO, and now there's a new methodology. Let's have a look. So you know the good old proximal policy optimization here that was invented here by OpenAI a long time ago. And then we switched over to the direct policy optimization without any intermediary models. And now we have some odds ratio preference optimization. And we will have a look at this now in detail. So we start with a pre-trained LLM. And in the old case where we had this reinforcement learning from human feedback, you had the supervised fine-tuning, then you had a reward model and different policies that you optimize here in reference models. And when we switched to DPO, things became simpler because we skipped the reward model. And now we're here that we go directly from the pre-training here to the ORPO. And if you just want to know what it is simple. We have here chosen responses that we like to enforce and rejected responses in our training data that we'd like to reject. This is all there is to it. So I know what you're going to ask now. You say, so is it more or less now a DPO or is it more or less an SFT? Well, yeah, just to explain why it's called an odd ratio model, but it is a preference-aligned supervised fine-tuning. And a lot of you asked me when I showed you here my DPO video, and you said, do we have to have still the supervised fine-tuning step here from our pre-training model? And I told you, yes, you need here for the specialization in your downstream task, like summarization or translation. And now we, if you want, take the DPO idea, the DPO alignment, and we have now a new preference alignment supervised fine-tuning. So beautiful it is that we have a reference model free, monolithic, odds ratio, preference optimization algorithm, ORPO, and it eliminates yet a necessity for an additional preference alignment phase. So things become simpler, but also better. Let me show you why. Yeah, of course, the models here are available from our colleagues here from the South Korean Institute for AI, and you have it here at KAIST AI. They used the Mistral 7B model, they trained it, or they ORPO preference aligned here in the supervised fine-tuning phase, my goodness, on the data set here of the ultra feedback, the binarized version. So here you have it, the Mistral 7B, ORPO preference aligned SFT, my goodness. So you can download from Hugging Face and then you just go and you have the dialogue ready for you and you can experience if this is the model for you, if your specific tasks are covered here in the content of the ultra feedback dataset. If you don't remember anymore what it is, we had easy. This is here the first example from Hugging Face here from our ultra feedback dataset. We have a prompt like, how can I develop a habit of drawing daily? And then we have here a chosen answer that we want the system to take and that to simulate this kind of an answer. And we have the rejected answer that we do not want the system to emulate and come back in this particular way. Beautiful. Yeah, here you have it now, the publication. Please note we go with version 2 of this research paper with some correction and some more beautiful things from March 14, 2024 from KAIST Artificial Intelligence. And as you can see here, if you go with the Llama 2 model and you have here the reinforcement learning from human feedback, and then you have in blue then ORPO, you see it's better than those. And if you go with a Mistral 7B and you have here in green the DPO aligned phase, you see with the ORPO, if you want to call it aligned supervised fine-tuning, we get an even better performance. But notice here, the increase here is not as significant as you might think of. So how they do this? What are the benefits? Yeah, just wanted to show you here the South Korean Advanced Institute of Science and Technology. And they have a lot of faculty member, world-class faculty member. And they were just founded and established here in the fall of 2019. So now let's talk about here the equations. You know, we have here the cross entropy loss. And we have here the model fine-tuning phase. And what we do normally is here exactly here for our loss function, and you know this. Now, however, using the cross entropy alone gives us no direct penalty or compensation for the losses of non-answer tokens. So while cross entropy is generally effective for some domain adaptation, for some domain specialization, we still have within this, if you want, fine-tuning process, a lot of things that we do not want to fine-tune on. So what they call here, what they should reject right at the beginning and not go through the supervised fine-tuning where we have some elements we do not want. And then in the alignment, DPO alignment phase, we have to get rid of those. So the idea is here, within our supervised fine-tuning, only enforce the behavior that we want, even in the fine-tuning. Beautiful. Yeah, if you want to go there, there's of course a Hugging Face, a GitHub for you. And here you have all the models and all the benchmarks and everything for you if you want to go immediately and check it out. But you know, we have to add here some corrective term to our equation, to our loss. And if you want to have a detailed look in this, you find this here in the literature. But maybe let's start with some simple idea from physics to go there and understand what happened here in this particular case. So we start very easy for my green grasshoppers. My goodness, this should be green. We have the loss function. And in machine learning and deep learning, a loss function quantifies here the difference between the predicted outputs of the machine and the actual target values. And you know the goal is simply a minimization and optimization of the loss function through the adjustment of the model parameter during the training, improving here the model accuracy and the predictive performance. And the loss function, often we have here this L of theta, where theta represents a parameter of the model, is a scalar value, optimize the algorithm seeking it to minimize. And for a regression task, we have here mean square error, and for classification task, we have the cross entropy. You know this. Now, interestingly, in physics, we have something real similar. And it is called the Lagrangian from pure mechanics, and we have there also an optimization program. Classical mechanics, you have a Lagrangian where you have the generalized coordinates, the time derivatives, and the time itself. So this is a function that characterizes the dynamic of a physical system. It is easy to calculate. You have an action integral. Beautiful. And what you do now, you can optimize this in theoretical physics, particularly in a constrained optimization. The Lagrangian is a function designed to find the extreme value of a function subject to some equality constraints. For example, you can have different boundary conditions, or you can have system inherent constraints that you have to take care for in the optimization process. Now, the connection between both. So we have the loss function in artificial intelligence, and the Lagrangian in classical mechanics and theoretical physics. Both optimization share here this common goal of an optimization of a system. And this means in both cases you want to minimize a certain quantity of your system. In artificial intelligence, it's about minimizing the error of the loss function, while in mechanics, it's about minimizing here the action. And in a constrained optimization, about finding here the minimum of a function subject to these particular constraints that we have on our physical system. So both domains leverage here the calculus of variation, which deals with finding functionals. This means function of function that extremize here a particular quantity. So, you know, machine learning training involves adjusting a model parameter to minimize the loss functional. And in classical mechanics, the path of a system is determined by minimizing the action functional. Hey, isn't this beautiful? And you know, there's even more analog. Because if you look at gradient descent on our Lagrange equation and the optimization techniques used to minimize the loss function in AI, such gradient descent, it is really quite an analog to the method we use here in theoretical physics and mathematical physics to solve the Euler-Lagrange equation in the classical mechanical case. Provides the conditions for the extremization of the action integral. Plus, going now one step further, you remember we have in machine learning regularization terms that we add to our loss function. And you're not going to believe it. This is quite similar what's happening now. So just short summarization, what was here regularization used in machine learning to prevent the overfitting of a model complexity? It involves adding an extra term to the loss function, which represents the complexity of the model. And the aim is to balance the trade-off between fitting the training data well and maintain the model ability to generalize to unseen data. And you know here the mathematical formulation, the loss function with a regularization term is given exactly by this equation, where L of theta is here our original loss function, and R, the regularization term here, is given here with a particular parameter, lambda. This is the regularization coefficient that controls here the strength of the regularizations. And you notice, and here's a little bit additional information for you. Now, let's compare this again, AI and theoretical physics. And yes, you get it, because if we move then to quantum computer AI, we need to work with physical system. Okay, so here we go. Classical mechanics, the Lagrangian itself does not inherently include a concept analogous to regularization. However, in the broader context of optimization, particularly in the constraint optimization, the Lagrange multipliers here are used to incorporate here constraints into the mathematical optimization problem. And this can be seen as being quite similar to the regularization in the sense that both mechanisms introduce additional terms to influence here the optimization process. And yeah, maybe you know here the Lagrangian here, it combines now the objective function f of x, here f of x, to be minimized here, and a particular constraint function through the Lagrangian multiplier lambda. And we will use this idea from mathematical physics to do here our ORPO optimization in AI. So now you have an idea that it just not happened overnight, but those are ideas and ways that we proceed in theoretical physics if we have the objective function that we want to minimize. Of course, it is not absolutely the same, but the tools and the mathematical ideas that we use, they are quite similar. You should be familiar with this. Yeah, for my green grasshoppers, if you don't know the role here of a Lagrangian multiplier, this is here a little bit of a mathematical fresh up. Beautiful. Now, in parallel, I have a problem. I sometimes go there to LM-sys, and I says here, for example, I've chosen an almost 7B instruct model, and I ask, hey, is a loss function in AI and a Lagrangian of a physical system somehow connected? And I have to say, I was impressed by this answer by ORPO. I've never worked with this before, but I just want to tell you, for a 7B model, there are some real clever ideas. Is it 100% correct? There is some interpretation, but in general, a very nice system. Compare this to a Llama 2 70 billion free trainable parameter model, so 10 times as big. And I have to tell you, 0.4, the Legendre transform, this is not what I would go with. This is from a very particular idea that's somewhere in the vector space that the system decided here. Okay, let's take this in, but this is, you have to understand theoretical physics to understand where this particular function comes from. So even if you say, hey, Llama 2 70B, this must be the correct answer. 1, 2, 3, yes, in an interpretation, but 4, I would be really careful to use this for further understanding here. So what is it really? We go back here to our conceptual connection here. So both the regularization terms in machine learning and the constraints in the optimization theory guide now our optimization process towards our desirable solutions in a high-dimensional space. Regularization by controlling here the model complexity to avoid overfitting, and constraints of our system here by ensuring solutions that adhere to specific conditions, boundary conditions, internal conditions, whatever we have. And of course, you have now some hyperparameters because you have to balance all of those things. So just as regularization involves balancing the fit of two data with model complexity, incorporating constraints to the Lagrange multipliers, now involves balancing the objective function with the need to satisfy constraint equation. So both mechanisms introduce a form of a trade-off in our optimization process. And this is something beautiful. So it gives you a little bit of a mathematical, physical background knowledge why we are doing this, and that it is absolutely okay if you do this. Okay, so now let's move over that we understand a little bit of the mathematic background here to our odds ratio preference optimization methodology. And let's have a look at this now in detail. And here we have it. Here we have now our objective function. And our objective function here has now two components. The first one is here the loss function that you know. This is here from the supervised fine-tuning loss function that you are familiar with. And then we have, and notice here what a coincidence, we have here also a lambda. We have a correction term. We have an additional constraint that we imply on our physical system. So, yeah, the classical supervised fine-tuning follows the conventional causal language modeling negative log likelihood loss function to maximize the likelihood of generating the reference tokens. But of course, we are interested here in our additional term here, and what a coincidence that it's lambda again. So what is this? There is also called a penalty. What is this? This penalty for unwanted generation styles is designed now to discourage the model from producing here what we called disfavored outputs, a style that we do not want. And as I just showed you, this is simply by incorporating an odds ratio based penalty into our loss function, which quantifies here the preference disparity between the favored and the disfavored response. So with your lambda parameter, you are here in control. It's kind of a hyperparameter in our optimization problem. And the aim is to optimize the model not only for accuracy in the following instruction or generating correct responses, but also to align its output here with specific stylistic or content-based preferences, as we have shown you here in the training data set. So this ORPO loss function is now something very specific, and it integrates now this penalty that we have normally in our DPO algorithm directly into its objective function alongside the conventional supervised fine-tuning loss that you know. And the total loss is thus a combination, you're not going to believe this, of the classical term and the additional term. Okay. Now, going back for a moment here to machine learning, the regularization, as I told you, regularization machine learning is used to prevent the overfitting and to promote the model generalization to unseen data. And now by adding here the penalty term to the loss function to regularization, encouraging the model to keep its parameters small or sparse, depending type of the complexity of the regularization applied, limiting the model's complexity. So you see, it is kind of similar to the idea of a regularization term. But now we apply it, if you want here, from the DPO alignment phase, and we integrate it here directly in our supervised fine-tuning methodology. If you want to have a little bit of a deep dive in the conceptual similarity, I have here 3 paragraphs for you. Important is, just as the strength of the regularization is controlled by a coefficient, the impact here of the ORPO penalty is also subject to tuning through hyperparameter to determine the weight of the penalty relative to original loss. So you have here an option, an additional hyperparameter that you should definitely investigate. So here you have it now. And as I showed you at the very beginning of this video, it is not really a simple idea, but the basic of this idea is what we always do when we have optimization problems in theoretical physics. Now we just apply it here in a kind of a simplified version here to our new supervised fine-tuning with the special odds ratio alignment process put together. So in summary, while specific goals and implementation of ORPO penalty and regularization terms in machine learning differ, they are in-depth different objects, but they, from the concept, operate under the same or the similar premise to modify here the optimization landscape to enforce here some additional desired property like the style or the way you want your system to behave, or the constraints here on the solution, thereby enhancing the model's alignment with some broad objective or prevent undesired behavior. And this is exactly what our colleagues here from Case AI have done. Now, if you look here for some benchmark data, and please note we have here in solid green and solid blue, here we have our Mistral ORPO aligned supervised models for the Mistral 7 billion free trainable parameter model. And you see, okay, writing humanity, STEM, yeah, extraction, role play, but there is a problem here, definitely, if you compare it here. This is GPT-4, of course, here in the outskirt. There's something missing here on math and coding and reasoning. Please notice this GPT-4 in reasoning is, I would say, at a 9, while our Mistral is somewhere at a 5+. So there's some significant difference. But at first, think about the size of the model. It's a 7 billion free trainable parameter. And then for this particular model, remember that we used here a very particular training data set. And if you check this training data set, you will know that it lacks, it's missing here all the coding and mathematical skills in the data set. So how the hell should it know how to do this? So you see, this is here a direct reference to the missing training data. But with writing and humanities and role play and extraction, yeah, there's a lot of data. So if you just add here now for ultra feedback, mathematical or logical reasoning or coding, you would get real nice performance now. And you have a new methodology to go from your pre-trained LLM now to your final stage LLM. Beautiful. Yeah, what I wanted to show you, I think this here, this is figure 7 here in the official publication by Case AI. This is something really nice because you want somehow to make sure that the chosen type, as I showed you in the dataset, is really enforced and the rejected part is really going down so that the function that we want here from this additional regularization term or Legendre function, we want that it works. And here we have now in figure 7 here in green, you see that the chosen, yeah, this goes up. And what we want, that the amount of rejected answer is going down. And this is exactly what's happening if we increase the training step. So they have shown that this system works. It is the very first day. Of course, it's only a prototype and it is not included in the Hugging Face optimization libraries. But I think this is really nice. In the next weeks, I will try an experience here with this ORPO. Maybe I give you some feedback from my personal data, from my task that I have. But it shows us here that this ORPO functionality is successful preserving here the domain adaptation here, this role that we have and why we use here our standardized or supervised fine-tuning methodology, while the penalty times here term of our loss function induces the model to lower the likelihood of unwanted generation of unwanted style or unwanted behavior, what we normally have in our pure DPO phase. So some interesting development, real nice idea coming from mathematical physics here to implement this in a way. But of course, we only have a 7 billion trainable parameter model. And if you want to scale this up, I think we have not enough data. If you really should switch right now, give it a little bit of time. There are a lot of optimization going on. But the idea to have in your pure supervised fine-tuning already an optimization taking place, plus an alignment, this is a beautiful idea.